Hello everyone, I'm Tom, and in this video I'll be telling you a bit more about word embeddings, what they are, what they're good for, and how they relate to social issues such as gender stereotyping. The context of this video is formed by the DADD Language Bias Visualiser, which is a tool to interactively compare male and female stereotypes inherent in large textual datasets taken from the internet and captured by word embeddings models. As a technique, word embeddings are at the intersection of several fields in computer science, the first of which is AI. The goal of AI is to create systems that behave intelligently and independently. Second, within the field of AI, machine learning, or ML, is a group of strategies that model data and attempt to extract valuable information from that data. Within machine learning, there's also the so-called field of deep learning, which often makes use of artificial neural networks in order to automatically discover the representations needed for feature detection or classification. Finally, word embeddings take from natural language processing, or NLP, which is concerned with the interactions between computers and human natural languages, particularly how to program computers to process and analyze large amounts of natural language data. For now, what you need to know is that in conjunction, these fields can produce a model for us that is called a word embedding. What is a word embedding? Basically, it's a model in which any given word can be associated with an array or a vector of numbers. And it's not just any vector, but it actually represents something about the meaning of any particular word. Now, why would we want to do that? Well, it allows us to do things with words we wouldn't otherwise be able to. Things like math, adding, subtracting, multiplying, and so on. This here is perhaps the most famous example. If we have a word embedding model with a vector for the word king, and we subtract from that vector the vector for the word man, while adding the vector for the word woman, the resulting vector will be closely related to the word queen. Now, in order to appreciate how exciting this is to NLP researchers, you should know something about how words are typically represented by computers. Typically, NLP uses forms of discrete representation, as it's called, which is usually done using one-hot vectors, such as the one you see here. Basically, 1, 1 and lots of zeros in a vector, which represents all word types in some vocabulary. How many zeros? Well, that depends on the vocabulary size. Vocabularies of a large language dataset can contain anything between 20,000 and tens of millions of words. So that's a big vector. Now, the problem is, even though we have a numerical representation of the word cat here, it doesn't help us much. If you know anything about linear algebra, for instance, you might say, well, that's interesting. We have a vector for both the word cat and now for another one, say kitten. Can't we do anything with these two vectors? For instance, couldn't we calculate the dot product? But that's actually something you can't do because there's no notion of similarity between these two vectors. So this representation doesn't really tell you anything about the similarity between words. So the question becomes, well, how can you encode word relations in these vectors? This is where one of the most important hypotheses in NLP comes in. It's simple but profound, and the English linguist J.R. Firth put it well: you shall know a word by the company it keeps. This is the idea that the meaning of words is understanding their uses. If you understand the context of a word, you understand the word itself. Now, this is not an uncontroversial way of defining word meaning, but it actually turns out to work quite well in NLP. If we would define this as a machine learning task, We could say, well, let's find thousands of instances of words and their context. In this example, which is about the word cat, let's find all kinds of things about their physical features, their behavior, their history, and so on. Here you just see two of such sentences in which the word cat may appear. And we could then use all those sentences to represent the meaning of the word cat. So we have to get away from one-hot encoding. And in a word embeddings model, all words are represented by what's called a dense vector, like this. That means not a bunch of zeros and a 1, like we just saw, but a lot of values in one vector for every single word. Theoretically, if we use such a representation, we can start looking at similarity measures, such as the dot product of this particular vector. Finally, and this is where this becomes a machine learning or prediction task, we can try to teach a machine how to predict the similarity between these vectorized words by nudging all these vectors in some learning model so that they become better and better at being predicted by the others. What this yields, in short, is words that are able to predict their contexts and contexts that are able to predict words. One of these deep learning models is called Word2Vec. And Word2Vec is actually not a single algorithm, but a combination of two deep learning techniques, the so-called continuous bag of words and the skipgram models. So in the continuous bag of words and skipgram models, we either try to predict the probability of a word given a context, or to predict the probability of a context given a word. How do we do that? Well, we do that within a particular window size or radius of each word, which is basically a hyperparameter that we define ourselves up front. Third, as is typical in machine learning, we make use of a cost function, which is basically a way of telling our AI system where it can improve its performance. This is what we do in ML, right? We try to make an algorithm better at predicting something. To do that, we have to be able to tell it when it's screwing up. And the goal here, just to remember, is to maximize the probability of any context word appearing given the current center word. Or the other way around, maximizing the probability of a center word given a certain context. Here is one example of the skipgram model, where we try to predict the context given some central word. The learning task is basically, there's a probability of some word appearing in that context, and we try to maximize that probability. So for each estimation we want our neural network to make, we have one word and we try to predict the words in its context, based on some window size or radius m. In this example, we're just using a window size of 3. The task that we give our neural net is, given a specific word in the middle of the sentence, also called the input word, the red word here, look at the words nearby and pick one at random. And our neural network then is going to tell us the probability for every word in our vocabulary of being the nearby word that we chose. Now, the output probabilities that we get from this are going to relate to how likely it is to find each vocabulary word nearby our input word. So if I feed in the word cat, it's going to be more probable to find words like litter box and paw than guitar or tank. Next, we have that cost function that tells us if we're doing well. In this case, our cost function j can be defined as 1, which would be a perfect score, from which we deduct the probability of any word that is not our central word at index t. The point, of course, is that if we can predict those words perfectly from t, we would have no loss. So our goal is to change the representations of words so as to minimize loss. Now, what this actually yields at the output of our model is one big probability distribution per word, which is that of the context words within which it is likely to appear. Basically, we first build a vocabulary of words from our training documents. So let's say we have a vocabulary of 10,000 unique words here. We're going to represent an input word, like the word ants used here, as a one-hot vector. This vector will have 10,000 components, one for every word in our vocabulary, and we'll place a 1 in the position corresponding to the word ants, and a 0 in all of the other positions. In the output of our model, where we evaluate its performance, we will then get a probability of all the words in our vocabulary being near the center word. Remember, that's our prediction task here. So again, the output of this neural network is a single vector, also with 10,000 components, containing, for each word type in our vocabulary, the probability of that word to appear in a randomly chosen position around the center word, though still inside the window. So the output probabilities are going to relate to how likely it is to find each vocabulary word nearby our input word. Now, how do we get there? Well, basically we calculate dot products of the hidden layer vector, i.e. our input word, with the output vectors, i.e. the output words. Now, this was a very short introduction, so if you want to know more about how this particular type of neural network works, I can heartily recommend this post by Chris McCormick. Now, you might have heard of things like Word2Vec or BERT. What are these? Well, they're simply different methods to generate word embeddings models, using different ways to represent the words. Word2Vec is just one method, and it's actually the one that we use in our language bias visualizer. Word2Vec was created and published in 2013 by a team of researchers led by Thomas Mikolov at Google. Now, you should know that Word2Vec is not the latest and greatest method. There's a lot of work going on in the field of word embeddings, and new methods are following each other up quickly, each with their own advantages and disadvantages. So, to summarize, word embeddings designate a process where words from some vocabulary are mapped to vectors of real numbers. They are numerical representations of contextual similarities between words. Second, this means that words that have similar meanings or that are used in the same context are represented by similar vectors. This is what that looks like visually. As you see here, the vectors for man as compared to woman are similar to those for king and queen. The same goes for verb tenses. The similarities in the vectors between a gerund and a past tense, for instance, is similar across words. Finally, word embeddings can capture relationships between objects. For instance, the relationship between countries and their capitals is very similar across multiple countries. So we could ask a word embeddings model something like, Madrid is to Spain as X is to Italy, and the model would know to respond that X is in fact Rome. Now, since a language model captures commonly associated meanings of words, it is not hard to imagine that this may include meanings that could be described as stereotypical or biased. For example, if in a corpus of texts that we're learning a model from, most of the leaders are described as men, and most of the assistants as women, then the vector of the word leader will be closer to the vector of the word man than to the vector of the word woman. When such biases sneak into our language models, this can obviously be an issue. Think of a virtual assistant trained using word embeddings that may give biased job recommendations for women versus men. However, we can turn this around as well. The interesting thing about word embeddings and language models in general is that we can use them in order to trace language bias in particular datasets. Recently, several projects have been launched that use NLP in order to figure out whether language is biased or stereotyping. One example is the gender decoder for job ads, which allows you to enter a job and it will tell you whether there is linguistic gender coding present by calculating the relative proportion of masculine coded and feminine coded words in some preformed word list. Here's another example which allows you to input any text and have it check for a hidden gender bias, again based on a preformed word list. So how can we trace these kinds of biases using word embeddings? In the next video, we will show you how our language bias visualizer works, and how it allows you to scrutinize biased language about gender in different online datasets.